Start.
All right, so we can start with Lecture 10. So my last lecture, I ended up talking about tissue edema. And if we just turn back to plate 40 for a second, that in that plate there is lymph flow. And so I'm going to talk to you about the lymphatic system, and that's on plate 41. So it's like in the initial design, we set up all these tubes, to carry material from the ventricle back to the atrium, kind of contain this fluid. But at the same time, we had to have exchange. We needed to get material exchanging between the blood vessels. And that involved filtration and reabsorption. And in the perfect world, the amount of reabsorption in the interstitium would be the same as the filtration. So you would have no net movement. Well, turns out that's not how it quite works. That even in muscle tissue, which has relatively non-porous capillaries, certainly compared to the fenestrated capillaries of the kidney, there is net fluid loss, net filtration. So how do you deal with the fact that you're putting fluid out? The body has a separate set of tubes called the lymphatics. The schematic of the lymphatics is given right here in the overall view of circulation. So here's your heart. Fluid is flowing out the arteries, going into the capillaries, and then at the capillary levels, there tends to be some net filtration. And so you see, they give you numbers. And again, the numbers aren't important other than to reflect the volumes of fluids that are exchanged. And these are values for humans. They're going to be smaller for our small domestic animals, larger for our large domestic animals. The net effect is that you have net filtration. That this arrow coming out, net, is going to be greater than the fluid going in. So unless you do something with that fluid, you are going to have tissue edema. This fluid is picked up by a separate set of blood vessels, a separate set of vessels. They're not carrying red blood cells, right? These aren't cells. These are fluid going into what are called the lymphatics. Lymphatics are characterized by being blind-ended. That is, instead of being a nice circuitous circulatory system, one end is closed off. They also have one-way valves, so that fluid that's moved up can't flow back into the tissues. All of this fluid, excess fluid, is collected in these lymphatics that drain into a common vessel called the thoracic duct. And your text doesn't give it a name, but it's called the thoracic duct. It feeds into the vena cava. So it's coming back into the venous system and returns that fluid then to the vascular channel. And the value in humans is 8,400 liters of blood. It says, of the 20 liters that filter out of the capillaries into the tissues, some 18 are returned by reabsorption in the capillaries. That still leaves you with 2 liters of fluid that, unless you had the lymphatics, would accumulate in the interstitium. So lymph capillaries, very porous. They allow this free exchange of material. They have one-way valves but no muscles, where the force for this movement comes from is by contraction of the peripheral tissues. So you have lots of lymphatics in your muscles. As you move and contract, these muscles squeeze the lymphatics. So here's our view right here. Material coming into the lymphatics, squeezing of the tissue, then forces the blood, or forces the lymph in one direction. One direction because one end is closed and you have these one-way valves. What happens if you don't contract your muscles? What happens if you sit for a long period of time? Fluid accumulates. You get tissue edema associated with that. In addition to some of the fluid loss, there is, in fact, some protein lost. Now, we pretended that proteins were large. They didn't diffuse out. There is a small, but again, over time, significant loss of proteins. We see not only the fluid being returned to the vascular channels, but also the protein. So lymph functions in fluid and in protein. Lymph also plays a very important role in fat transport. When we talk about the digestive system, we'll talk about that in detail. And we all know about lymph nodes. Lymph nodes are large collections of lymphoidal tissues. They play a seminal role in immunological defense. It is the site for most of the lymphocyte production. Certainly the T lymphocytes that you'll learn about in lab congregate in these nodes, so that they play a very important role in holding and moderating the white cell population. Let's return to the circulatory system and talk about the venous system. So we've walked from the heart through the arteries, through the precapillaries to the now to the venules into the veins. Two important roles. One is that they're very low resistance. Pressures on the venous side very low. When we measure, and really what's involved in perfusing tissue is the pressure difference. And since the venous side is very low, most of the regulation comes on the arterial side. So that's kind of why we've been talking and stressing the importance of arterial blood regulation. But that only occurs because veins are very low resistance. Well, they're low resistance and they have a tremendous capacity to change their volume. They can change their volume without much change in pressure. They are very compliant. So if somebody says you're not compliant, that means you're not very flexible. You can't expand. You can't store a lot of stuff. But compliant vessels can expand their volume and change the pressure very, very little. So if we're looking at blood pressure in the veins and it's maybe 5 millimeters of mercury, we can expand the volume without changing that pressure. That means that the pressure drop across the arterial circulation doesn't change much. The consequence is that the veins can now be a huge storage reservoir for blood. And again, the numbers aren't important for us. I think merely the magnitude. Excuse me. Give me a second as I remember. There we go. So this top cartoon gives you an impression of the magnitude of where the blood is found. I've really kind of not talked much about the pulmonic circulation. We will talk about it. It's not that it's not important. We don't measure blood pressure in the pulmonic circulation commonly. Not a lot of lymphatics, as we'll see, but only 11% of the blood is stored in the lungs. So very small circulatory volume. Smaller mass, right? Lungs this big, rest of your body, all the periphery. So that merely reflects the fact that there's not as much tissue to perfuse. It's still got 5 liters a minute going to it. It's important exchange properties, but not as much. Left side of the circulatory system, capillaries, shows only 5% of the blood being in the capillaries, and that the venous circulation has the vast majority. Sitting at rest, non-exercised. How can it do that? That's represented in this graph right here, which is pressure versus volume. We said the capillaries could expand their volume with little change in pressure. So this is a schematic diagram of the veins, very compliant. Arteries, not as compliant. So the slope of this curve, change in volume over change in pressure, we refer to as compliance. I'm sorry. This is, just to confuse you, this is pressure versus volume. So the slope of this curve is change in volume. Rise over run. Pressure over change in volume. This has a lower change in pressure for a given change in volume. So this is a very compliant vessel. What happens during exercise? Veins have smooth muscle as well, muscle that is innervated by the sympathetic nervous system. As these muscles contract, they force this blood volume back into circulation, circulating to the tissue that needs it, now to the skeletal muscle. What else happens during exercise? Muscle contraction. We talked about muscle contraction and lymphatics moving fluid through the lymphs. It also helps to move fluid through the veins. Like lymphatics, veins have valves. These valves direct fluid flow back to the heart. So one of the ways to increase venous return then is by contracting your muscles more and more. That helps move the fluid back. What happens if you lose those veins? Lose those valves? Varicose veins. So these people have these hugely distended veins. Oftentimes these are superficial, right? But it's because of a breakdown in that valve, and so the contractile tissue around it doesn't help it to move. So we have venous return by pressure gradient. We have venous return by muscular pumping. And the last mechanism for helping return blood flow is what is called the respiratory pump. So here's our heart lying in the thorax. It's defined by the thoracic wall and by the diaphragm at the bottom. During inspiration, the diaphragm contracts, so it moves down this way. The chest wall expands so that the volume becomes greater in the thoracic cavity. PV equals nRT. In a closed thorax, if the volume goes up, what must happen to the pressure? It decreases the pressure in the thorax. That decreases the pressure on the veins, and so the veins in the thorax, primarily like the vena cava. So what does that do? That actually increases blood flow back into the vena cava, into the atrium during inspiration. So every time you inspire, you help pump blood into your vena cava. This also shows that while the volume of the vascular cavity, the thoracic cavity is going up, volume is decreased. You're kind of pushing your guts, and what that does is that pushes against veins in the abdomen. So you're reducing the pressure in the veins in the thorax, you're increasing the pressure in the veins in the abdomen, because the one-way valves, what does that do? That helps blood to flow back. So we've talked a lot about control of blood flow through sympathetic and parasympathetic. We're going to come back and talk about that. But what I'd like to now is talk about local and systemic control of small blood vessels. Flow is a function of pressure and resistance. Our major control over resistance in these tubes is by changing the diameters. The major site of resistance is the arterioles. The arteriole are made up of endothelium and smooth muscle. These tissues are very responsive to the production of local chemical factors. Well, what's being produced in these tissues? Let's consider muscle tissue. That should be up here. So this is skeletal muscle. It's being active, and it's producing chemicals of metabolism. It's producing things like lactic acid. It's producing CO2. It's decreasing the oxygen. The smooth muscle of these arterioles are sensitive to changes in the acid, changes in the CO2, and O2. And all of these are potent vasodilators. So the arterioles and meta-arterioles can respond to the local activity of the tissue. And it is preeminent in skeletal muscle. So in fact, blood flow to skeletal muscle is controlled in large part by the production of these local chemical factors. So in a non-exercise state, these factors, low lactate, relatively low CO2, high O2. The vessels are constricted and you're shunting it elsewhere. Now think about exercise. Exercise increases lactate, CO2, the vessels dilate. At the same time, what's occurring with the sympathetic nervous system? Causing the venous system to contract, so it's pumping, it's increasing venous return. It's vasoconstricting tissue that doesn't need it, like the gut, the kidneys. So now the blood flow that is made available from a reshuttling or shunting of that blood from those unimportant tissues can now go strictly to the muscle. One of the terms I want to introduce you to here is first to vasodilating substances released by ischemic tissues. Ischemia means compromised or decreased or no blood flow to a tissue. Ischemic tissues are doing what? They're still metabolizing. You're just not recognizing it and carrying away those CO2s. You're not carrying away the lactic acid. So in fact, these same metabolites that occur during an active muscle also occur in ischemic tissue. And one of the big problems with ischemic tissue is also the production of what are called oxygen radicals. So as this poorly perfused tissue becomes more and more compromised metabolically, you have a buildup of all of these chemical compounds. Well, if they can override and get blood flow to the tissue, that's great. But so what happens if you have like a twist, say to the gut, and you have a buildup of these? Then what happens is, if you are able, you go in and surgically re-establish the blood supply. You untwist it. Now all of a sudden you have huge concentration of these chemicals, and you can actually get what's called reperfusion injury simply because of the buildup of these all toxic compounds. And so it becomes a critical issue. Do I take the tissue out, or do I try to reestablish blood supply? Nitric oxide is a chemical that we're recognizing more and more. Nitric oxide plays an important vasodilatory role. It says continuous production of NO has been implicated in the maintenance of normal blood pressure. So not only we'll talk about it when we talk about Viagra and its impact on nitric oxide. But we see nitric oxide, NO, being produced in lots of tissue. It is a potent vasodilator. Okay, neuroregulation of blood flow. That I've spoken about. We're just going to re-emphasize that. Smooth muscle. Talked about the sympathetic innervation of this. We talked about alpha receptors, vasoconstrictors. So this shows normal sympathetic activity, less impulse, less vasoconstriction. You then move to the more relaxed, so this is the vegetative state. We talked about balance between sympathetic and parasympathetic. The ultimate response is going to be a function of those two neural networks. You can increase the sympathetic response by simply increasing the sympathetic response. The other way is simultaneously increasing the sympathetic response while decreasing the parasympathetic response. So the purpose of this is, under normal situation, you in fact have some parasympathetic activity occurring. That it's not all on or all off. Then, as you become more relaxed, so this is the individual down in the Caribbean, and they haven't got their visa bill yet. There's an inhibition of the sympathetic nervous system. So the parasympathetic system now is more active, and the vessels vasodilate even more. Low blood pressure. Now you get really angry. So this is the individual who's, and they're not exercising, shows them behind the wheel, road rage. Large amounts of norepinephrine being dumped in, large amounts of vasoconstriction. So what happens to this individual's blood pressure? Goes up. What do you think happens during exercise? We've talked about exercise, large amounts of sympathetic activity. So your sympathetic activity is going up, pushing the parasympathetic activity down. What happens to your blood pressure during exercise? Surprisingly, very little. Why? Because of local control. Those tissues are producing nitric oxide, CO2, lactic acid metabolites. That is an override, if you will, over neural control. So having large amounts of sympathetic activity during exercise is a good thing. It's a great thing. If your sympathetic activity goes on and unregulated, you will see elevations of blood pressure. Bo, can we take a break for a minute?
Yes.
Bo?
You can start.
Okay. Let's turn to plate 44. Control and measurement of cardiac output. We've talked about local control. Now let's take the big picture. Cardiac output is a function of heart rate, which is the frequency of beating, and the volume of blood which is pumped out with each contraction. That is referred to as stroke volume. And if I ever slow down, so this is the multiple approach. If I scroll too rapidly with this, all right. So in the upper panel, you see heart rate, beats per minute, times the stroke volume, which is liters per beat. That equals the cardiac output. And the number I've been using, 5 liters per minute, reflects resting cardiac output in humans. So for a 70-kilogram animal, that's a fairly reasonable volume. Well, what happens during exercise? We already have the tools at hand. Parasympathetic, sympathetic nerves. During exercise, sympathetic system goes up. That's going to increase rate and strength of contraction. Parasympathetic system is going to be down. Since parasympathetic tends to lower the heart rate, a decreased parasympathetic activity will act to increase heart rate, kind of double negative. So you amplify the response by having one system go up and the other system go down. You amplify the magnitude and also the speed. We've talked about sympathetic nervous system. Remember the adrenal medulla? Epinephrine is released from the adrenal medulla. Epinephrine has some very potent effects on acting by beta receptors to increase rate and force of contraction. So in addition to the sympathetic neurotransmitter norepinephrine, epinephrine is acting in an important role. The last thing on this page is measuring the cardiac output using the Fick principle. I'm not going to really talk about that. So let's flip to plate 45. I can find baroreceptor reflexes and control of blood pressure. I've talked about how you measure it. And to refresh your memory with the now famous flow equals change in pressure over resistance. This is a reformulation of this. What this tells you is the mean arterial pressure, which is reflected of delta P, equals cardiac output, which is flow, times the resistance. So this is merely a restatement of the same formula that we've used over and over again. So by changing the resistance of the peripheral system, we can have profound effects on flow. What about the pressures? Well, the idea is to regulate blood pressure constant. If you have huge changes in blood pressure, you can have huge changes in flow. Now that might be very important for skeletal muscle, but think about your brain. What if all of a sudden you decide, well, my arterial pressure doesn't need to be 100 millimeters of mercury, let's decrease it. Now all of a sudden, flow to the brain is reduced and you die. So, regulation of blood pressure involves continuous monitoring. These sensory nerves are called baroreceptors. So baroreceptors are modified neural tissue which perceives force or distension or pressure. These nerves are located in the aortic arch and carotid sinus. So in this diagram, here's the heart. The aortic arch, because the aorta comes out and arches around to go caudally. In this arch are located these baroreceptors. There are also receptors located in the carotid. The carotids arise off the aortic arch and provide blood flow to the brain. Underline the importance of these vessels in delivering blood and the importance of having sensory devices located on these blood vessels to tell you what the pressure is. Signals from these neurons are passed to the blood pressure control center, which occurs in the central nervous system, in the brain, one of the first levels located at the level of the medulla. Now, there can be higher sensory processing, that is, you can perceive that you have a high blood pressure, but by and large, decerebrate individuals can regulate blood pressure fine, thank you, simply because of the importance of the medulla in regulating blood pressure. That sensory input is integrated and then transmitted out via the parasympathetic and sympathetic nerves. So we can control blood pressure then by changing the activity of the sympathetic nervous system, upping it, decreasing parasympathetic. What's that going to do? That's going to produce vasoconstriction. I can go the other way. I can elevate my parasympathetic, decrease my sympathetic, vasodilation. And by changing then peripheral resistance, I have a great change over the control of blood. And I'm going to finish by skipping plate 46 and going straight to 47 to talk about other mechanisms of blood pressure regulation. So we've talked about this, the carotid receptors, the aortic receptors telling you about blood flow, blood pressure. What are other mechanisms? And I'm going to start with the renin-angiotensin system. So renin is a hormone produced by the kidneys. Why kidneys? How do the kidneys get it? 30% of the blood flow at rest goes to the kidneys. So the kidneys are poised to have a sensation of how much blood is flowing through them. In response to low blood pressure and low flow, renin is released. Renin goes into the general circulation where it confronts an inactive protein called angiotensinogen. Angio meaning blood vessel, tensinogen, tension force. So you get an idea what it's going to do. It's inactivated form, so it has no profound effect. However, in the presence of renin, it's converted to angiotensin 1. Angiotensin 1 circulates through the lungs, where converting enzymes in the lungs convert it to angiotensin 2 and 3. So let's see. We got the liver producing angiotensinogen. We got the kidneys producing renin. And we've got the lungs producing a converting enzyme. All with the purpose of producing angiotensinogen 2 and 3. Potent vasoconstriction. In addition, angiotensinogen 2 goes to the adrenals to produce the release of aldosterone. So physiologists, I mean, this is a wonderful essay question. Had one of these in my orals because it integrates so many tissues. What angiotensinogen 2 is not only vasoconstricting, it also stimulates the release of aldosterone. Aldosterone is released from the adrenals. Its target tissue is the kidney. So kidney produces renin. It's also the target tissue for aldosterone. Aldosterone increases sodium reabsorption. Well, when sodium gets reabsorbed, water follows. So think about the system that would activate this angiotensin-aldosterone link. Hemorrhage, loss of blood pressure. Blood pressure drops down, your kidneys release renin, you produce a vasoconstrictor that would tend to counteract that, would tend to up blood pressure. The aldosterone would increase the fluid reabsorption, so that would further increase vascular volume. The hypothalamus is also important in regulation of blood pressure in its role in regulating the secretion of antidiuretic hormone, ADH. Like aldosterone, ADH is responsible for an increased water reabsorption. The example here is thirst. If you're thirsty, you release ADH. It also occurs in hemorrhaging, loss of fluid. You can get release of ADH. So in addition to aldosterone as a hormone, you have ADH. The last hormone isn't really involved in hemorrhage, but is important in blood regulation, and that is atrial natriuretic hormone. Where is it produced? In the atrium. So another good place to sense volume. Natriuretic, so it has to do with sodium. So like aldosterone, it has to do with sodium. But the mechanism of ANP is in response to stress, excessive stress of the receptors. That's telling you the opposite of hemorrhage. It's telling you, I've got too much fluid. So ANP is released. It inhibits the renin, angiotensinogen, aldosterone, ADH. So all those things I talked about in hemorrhage are inhibited by ANP. So by keeping a balance of sympathetic, parasympathetic, that includes epinephrine, aldosterone, ADH, atrial natriuretic peptide, angiotensinogen, and having sensory receptors for all of these things underscores the importance of regulation of your blood volume and your blood pressures. And I think we'll stop there.